In this video, we talk about other tests for convergence of a series. We talk about absolute convergence and then ratio and root tests. We use absolute convergence test if signs of terms switch back and forth irregularly. And in this case, we apply the absolute value on the general term of the series, and that means we apply absolute value on each term of a given series, and so we make control over the negative signs or the sign of the series. So in this case we can study convergence regardless what the sign of a series is. So for absolute convergence, we say that a series is absolutely convergent if the series of the absolute value of an is convergent. And we have a result, an important result here. It's a theorem that says if a series is absolute convergent, then it's convergent. Let's take an example. For example, if we have the series sine n over n cubed, n from 1 to infinity, in this case we notice that this series has negative signs and positive negative signs of terms and positive signs. So, but this is not alternating series. So in this case we take absolute value of the terms. So we have series from n1 to infinity of the absolute value of sine n over n cubed, and then we study the convergence of the series because all terms here are positive. But here this is not the case. This has positive and negative terms, but it's not alternating series. Now we start with the following idea. We know that sine x in general is between -1 and 1. So sine of any value or any angle is between is from -1 to 1. It can be equal to -1, can be equal to 1 as well, and anything between them. So the absolute value of sine, let's use n here, sine n is less than or equal to 1. We can rewrite it this way, because if you want to rewrite this inequality without using the absolute value notation, you get this inequality. And then we try to formulate this series or this term. How to generate this term? We need to divide by n cubed. So we divide both sides by n cubed. And then we can take the series of both sides. So we take the series of both sides. Now we have a comparison. we can apply the comparison test here because we are comparing two series. Now if we look at the series on the right hand side, this is P. P equals 3. It's greater than 1. That means the series is convergent. So if the larger series is convergent, that means our series, the smaller series, is convergent. By the comparison test, our series is convergent. This series, sine n over n cubed, is convergent. And as you notice here, we took absolute value of the denominator as well, because this is always positive. So if we can take absolute value of the denominator as well, that will not affect our calculations or computations, and will not affect the test as well. So if the series of the absolute values of the terms is convergent, that means the series of the original series is convergent. So this is convergent. That means the series, original series sine n over n cubed, is convergent, is absolutely convergent, and hence it's convergent. By the comparison test. Now in general, absolute convergence implies convergence, but convergence does not imply absolute convergence. For the second case, we may think of the following series. The series -1 to n minus 1 over n. This is convergent because you can if you look at this series, this is alternating series. So for alternating series, you can take absolute value of the terms and find that this series is convergent, but this is the absolute value of these terms is absolute value of -1 to n minus 1 over n, and that is series 1 over n, but this is harmonic series. The power is 1, the p is 1, and that means divergent. So the absolute value of the series is divergent, but the original series is convergent, and we learned this in section 11.2. So this is an example of a convergent series that's not absolute convergent. In this case, we call the series, we call it conditionally convergent series. And actually, this is weaker than the absolute convergence. And in general, if the series is conditionally convergent, then it is convergent, but not absolutely convergent. As an exercise, you may think of this series. You can apply same technique as we did for the first problem to find that this is absolutely convergent series. Now we have a test that's called the ratio test. The ratio test for convergence. This test says that if limit of an plus 1 over an goes to infinity is equal to L, some number, that number is less than 1, then the series is absolutely convergent and hence convergent. Now if the limit as n goes to infinity of an plus 1 over an is equal to L greater than 1, that means, or let me add here, or if the limit is infinity, then the series is divergent. The third case, if limit a sub n plus 1 over a sub n goes to infinity is equal to 1, then the test is inconclusive. So this test is called the ratio test. This is the ratio test. We call it ratio because, as you can see here, we have a ratio. The ratio, absolute value of the ratio, a sub n plus 1 over a sub n, and we take the limit, the absolute value, and then the limit, and that should determine the convergence. Let's take an example. If we have this series 1 over n squared from 1 to infinity, we know that this is convergent because it's p series. The power, the p is 2 in this case. It's greater than 1. That means it's convergent. But using this test, let's try to see if we can apply this test or get some information by applying this test. So let's take the ratio an plus 1 over an and the absolute value. So we substitute n plus 1 here. So we get 1 over n plus 1 squared over, and then we take an as it is. It's 1 over n squared. And then we simplify. So 1 over n plus 1 squared times n squared, because we take reciprocal of the denominator. And then this is absolute value of n over n plus 1 all squared, and then we don't need the absolute value. Now we take limit of this. Let's take the limit. Limit of n over n plus 1 squared n goes to infinity. This is limit. We can insert limit here. N over n plus 1 all squared n goes to infinity. And as we know, this is equal to 1. So 1 squared is equal to 1. And that means we don't, if the limit of the absolute value of the ratio is equal to 1, the test is inconclusive. And if it's inconclusive, we need to try other tests. We may try the p series. This is p series, and we know that p equals 2 greater than 1. That means convergent. Now let's take another example. The series -1 to the power n times n cubed over 3 to the power n, and from 1 to infinity. Is this absolutely convergent? So let's apply this test. We're going to use the ratio test. So we need to find the ratio an plus 1 over an and then take the absolute value of that ratio. So an plus 1, we plug n plus 1 here. So we have negative 1 to the power n plus 1, n plus 1 to the power 3 over 3 to n plus 1. This is the numerator. This is a sub n plus 1, all divided by the original a sub n, negative 1 to the n cubed over 3 to the n. And then we take reciprocal of the denominator. We have absolute value negative 1 to n plus 1 cubed over 3 to the n plus 1 times 3 to the n over negative 1 to the n cubed. Now we can simplify. We know that if we have absolute value, we don't need the negative 1 to the power n plus 1 or the power n, because this is always positive. So we don't need absolute value because n is always positive, and negative 1 becomes inside the absolute value. The negative 1 will be positive 1. So we have n plus 1 cube this over n cube times 3n, 3 to the nth, over 3 to the n plus 1. Now we simplify. We can write this as n plus 1 over n all cube. And what about this? The denominator is 3 to the n times 3, and then we cancel 3 to the n. We are left with 1/3. So we take limit of an plus 1, absolute value an plus 1 over n goes to infinity. This is limit of n plus 1 over n all cube times 1/3, n goes to infinity. This gives 1/3 limit n plus 1 over n cube, n goes to infinity, and we know that we can insert limit here. So this is 1/3 limit n plus 1 over n cube, but this is equal to 1 as n goes to infinity. You can find derivative of the numerator, derivative of the denominator by applying the L'Hopital rule, and you get 1 over 1. So the answer here is 1/3. 1/3 is less than 1. 1/3 is less than 1. That means it's absolutely convergent. This is L. This is our L. So it's less than 1. That means, therefore, our series negative 1 to the n times n cubed over 3 to the n is absolutely convergent. One more example. The series n to the power n over n factorial, n from 1 to infinity, we apply same technique. We have an plus 1 over a sub n under absolute value. This is n plus 1 to the power n plus 1. We plugged n plus 1 here, times the reciprocal of an, it's n factorial over n to the power n, and then we simplify. So since all terms or expressions are positive, we don't need the absolute value notation. So we write n plus 1 to the power n plus 1 over n to the power n times n factorial over n plus 1 factorial. I rewrote it this way just to make simplifications easier. Now, by looking at okay, so I should work on, let's work on the absolute, on the factorial here. So for the factorial, we know that n plus 1 factorial is n plus 1 times n minus 1, up to 3 times 2 times 1. So we can rewrite this as n plus 1 times, instead of writing all these product, we just write n factorial. So this is n plus 1 times n factorial. And then, because you know that if you have 5 factorial, you can write it as 5 times 4 times 3 times 2 times 1, or you can write it as 5 times 4 factorial, because this is 4 factorial, or 5 times 4 times 3 factorial, and so on. And that's correct for n plus 1. If you have n plus 1 factorial, this is n plus 1 times n minus 1, etc. Or you can write it as n plus 1 times n factorial. This is n factorial. So this is the idea here. Okay, now since this is, we wrote the denominator as n plus 1 times n factorial, and we can simplify this. We can cancel n factorial with n factorial, and we get n plus 1 to the power n plus 1 over n to the power n times 1 over n plus 1. And here we can cancel. We know that this is n plus 1 to the power n times n plus 1, because the power is n plus 1. And then we can cancel this with this as well. So we get n plus 1 to the power n over n to the power n. This is the ratio. This is an plus 1 over an. Now we take limit of this. Limit an plus 1 over a sub n goes to infinity, is limit of n plus 1 to the power n over n to the power n goes to infinity. And this is, we can rewrite it this way, n plus 1 over n all raised to power n. But in this case, we don't insert this here because the power is n. It's not constant, so it still depends on n. So in this case, we can apply L'Hopital rule, because we know that if we substitute infinity, we get infinity to infinity. So we can convert this into one of the L'Hopital rule forms. So we write it this way. E to n ln, we can simplify this as 1 plus 1 over n. 1 plus 1 over n. Those are equivalent. Those two forms are equivalent, because if you want to rewrite it this way, you can bring power here. It becomes 1 plus 1 over n to the power n. And then you can cancel e with natural log and get that expression. So we take limit of the exponent because the base is constant. Now we want to write it as a L'Hopital, one of the L'Hopital's forms. So we can write it as natural log of 1 plus 1 over n over 1 over n. Those are equivalent. Those are equivalent forms. Now we have, if we substitute infinity, we get infinity over infinity. Now this is one of L'Hopital's forms, because the L'Hopital's forms are 0, 0 or infinity over infinity. So this is one of these forms. That means we can apply L'Hopital's rule. We find derivative of the numerator and derivative of the denominator individually or separately. So what is derivative of the numerator? Derivative of the numerator is, what is derivative of natural log? Derivative of natural log is derivative of the inside function or the inner function. It's negative 1 over n squared over same function. And then what is derivative of the denominator? It's negative 1 over n squared. So this is e to limit as n goes to infinity. We take reciprocal of the denominator. So we have negative 1 over n squared over 1 plus 1 over n times negative n squared over 1, and then we can cancel n squared with it and its sign. So we have e to the limit of 1 over 1 plus 1 over n, and as we can see, we can substitute n infinity, so this becomes 0. We get e to the power 1, which is e. E is greater than 1, that means this is divergent. If the limit gives us some value greater than 1, that means the series is divergent by the ratio test. Now the other test that's looks similar to the ratio test is called the root test. The root test, and we apply this test if we have some power or some, for example, nth power. So we have three cases. First, if we apply the nth root over the absolute value of the series, or absolute value of terms of the series, as n goes to infinity, and if that gives us L less than 1, that means the series is absolutely convergent, and thus it's convergent. Second, if limit of the nth root of absolute value a sub n goes to infinity is equal to L greater than 1 or infinity, then the series is divergent. 3, if the limit gives us number 1, the number 1, L is equal to 1, then it's inconclusive. The test is inconclusive. And as you can see, we call this test root test because we apply the nth root. Let's take some example. For example, if we have the series 2n plus 3 over 3n plus 2 raised to power n from 1 to infinity. In this case, we determine a sub n. A sub n is this expression. It's 2n plus 3 over 3n plus 2 raised to power n. And then we take the nth root. So the nth root, that will cancel this n here, the power n. So we cancel these to get 2n plus 3 over 3n plus 2, and that simplifies the computations. Now we take the limit as n goes to infinity of this general term, and we know that since this is infinity over infinity, this is one of L'Hopital's forms, then we can find derivative of the numerator and then derivative of the denominator to get 2/3. This is less than 1, and since it's less than 1, that means it's absolutely convergent. So the series 2n plus 3 over 3n plus 2 raised to power n from 1 to infinity is absolute convergent, and thus it's convergent. Another example, if we have the series negative 2n over n plus 1 or raised to power 8n n from 1 to infinity, we first determine a sub n, and here we can write the result is obtained by the root test. Now here we determine a sub n. This is a sub n, negative 2n over n plus 1 raised to power 8n. So we take the nth root of both sides. So taking nth root will give us, now we cancel this with this, and we get negative 2n over n plus 1 or raised to power 8. Now negative 2 to the power 8 times n to the power 8 over n plus 1 to the power 8. We take limit of this, limit of the nth root of a sub n, absolute value a sub n. I should take absolute value here. N goes to infinity, and here as well. So I suppose that the terms are positive, but we should take absolute value, and this is a good point to remind you that when we apply the test, we apply the nth root on the absolute value of a sub n. So we should have absolute value here, but since the terms are positive, we don't need the absolute value notation. So here we have limit of what is negative 2 to the power 8. Absolute value of negative 2 to the power 8 is 256 times n over n plus 1 all raised power 8. N goes to infinity. This is 256 limit n over n plus 1 to the power 8. N goes to infinity, but we can insert limit here because the power is constant, does not depend on the n. So we have limit n over n plus 1 all raised to power 8, but we know that this is equal to 1. Find derivative of the numerator, it's 1. Derivative of the denominator is 1. So we get 256, and that's greater than 1. That means it's divergent by the